Hi, I'm Pan from UCLA. In this video, I will present you our recent work on data-efficient optimization algorithms for reinforcement learning. RL is a sequential decision process where an agent interacts with the unknown environment to maximize its reward. In particular, at time t, the agent is at state st and choose an action at. Then the agent will observe a reward rt from the unknown environment, and it will reach a new state st plus 1. This process can be cast as a Markov decision process, which consists of a state space, an action space, the state transition probability that tells you how the agent moves from one state to another, and an unknown reward function. The goal of the agent is to find an optimal policy that tells the agent which action to choose in order to maximize its reward. This objective can be formulated as maximizing some performance function. The most common definition of performance is the expected cumulative reward that the agent can collect within certain steps. A fundamental optimization method is the gradient descent or gradient ascent. That is, we iteratively update the current policy by adding the gradient of the function j, and thus we obtain a new policy. Here, eta is the learning rate, and lambda j is usually called the policy gradient in reinforcement learning. However, it is impossible for us to directly use this updated equation in practice because the performance function is defined as an expectation over an unknown distribution that depends on the unknown environment. Therefore, we can only use a gradient estimator calculated based on empirical data. But in real life, it is often expensive to generate new data during the learning process. Then a natural question is, how can we efficiently estimate the policy gradient? Let's denote the sequence of state action state as a trajectory. By definition, J is the expectation of the overall reward on this trajectory. In order to estimate the gradient of J, vanilla policy gradient methods generate multiple trajectories, then use the average of the empirical cumulative reward as a gradient estimator to update the policy. This mountain color sampling method generates an unbiased estimator, and it converges to the optimal policy. Nevertheless, due to the high variance in sampling, the algorithm will oscillate a lot and converge slowly. Can we reduce the variance in the estimation of the policy gradient? The idea is to use control variant. In detail, the stochastic variance reduced policy gradient algorithm use historical data to reduce the gradient estimation of the current policy. In this new gradient estimator, pi old is a historical policy stored at some previous iteration. The old data was previously generated by pi old, and the new data is the samples we need to generate from the current policy. The extra two terms based on an older policy serve as a control variant, and it effectively reduces the variance of the gradient estimator and accelerates the convergence. Theoretically, we show that in order to achieve an epsilon stationary point of the performance function J, the total number of samples needed by stochastic variance-reduced policy gradient is orders of magnitude fewer than vanilla policy gradient. More illustratively, let's assume the required precision is 0.1. Then the state-of-the-art variance reduction algorithm only needs one-third of the data used by vanilla policy gradient, and if the precision is 0.01, SRVRPG only needs 10% of data used by vanilla gradient. This demonstrates the data efficiency of variance reduction in reinforcement learning. If you are interested in more details about our work, please refer to the papers listed below. Thank you.